In our previous lecture video, we had said, we're shooting something upwards, from the surface of the moon. It could have been any other kind of planet. We had the mass, we had the little mass, and it goes up some height. We solved for the r, and we came up with an equation that looked like this, in which we shot it upwards with some initial velocity v naught. Now, if you look at the equation, there's obviously a problem here. And that is, if v naught is 0, then obviously r equals r. Okay, so if v naught is 0, r equals r, it doesn't go anywhere, not a big deal. And then we said, okay, so v naught got bigger. Okay, so as v naught got bigger, then we found, that r was something, and we solved for it. But there's clearly a problem that exists here. Because if v naught is very big, r becomes negative. R can't be negative. I mean, that would mean that what's negative r? I mean, that's, you shoot it upwards and it ends up, inside the planet. That doesn't make any sense. Okay, if I can't be negative, because that would be, r is the distance from the center. How do you get a negative distance from the center? Because r is literally the magnitude of the distance from the center. That'd be like out of the universe someplace. Okay, and so, but we notice there's another problem. If v naught is just right, or just wrong, then 1 over r minus v naught squared over 2gm is going to be 0. And we're going to end up with 1 over 0. Clearly, that's a problem. Okay, so something is going on here. So that means we need to investigate this situation a little more carefully. Okay, so what we did before was just fine, but obviously if v naught is too big, something happens. Okay, so how do we solve this? K sub I plus U sub I equals K sub F plus U sub F. And so we look at it and we say, okay, so what's going on here? And so the farther away it is, the slower it gets, but then it stops and gravity pulls it back. So now the question is there a velocity here, initial velocity, such that it actually makes it infinitely far away and finally stops at infinity? So it takes an infinitely long time to get away, stops at infinity, and so in that case, the final potential energy is going to be 0. The final kinetic energy is 0, and so if you're going faster than that, it never comes back. In fact, it doesn't even stop. It just keeps going forever and ever and ever. If you're going that particular speed, it stops infinitely far away, but at that distance, you can't pull it back. So that would be this magical velocity that means that instead of going up, because you throw something up, it comes back down. So whatever goes up comes down. So you throw it up faster, it goes up higher, it comes back down. But this is saying there is a particular velocity that if you throw it up at that speed, it doesn't come back down. And if you go faster than that, it never even stops and it doesn't come back down. So we call that the escape velocity. So what we want to do is find the escape velocity. Well, to find the escape velocity, let's look at this. Okay. So the critical case is you shoot the thing upwards and it gets infinitely far away and stops. So the final kinetic and potential are both 0. So we have 1/2 mv squared. So this is our escape velocity, because this is the magic velocity right here. Minus gmm over r equals 0. Those little m's cancel, and so we can find the escape velocity is going to be the square root of 2gm over r. Okay, so now we have an equation that gives us the escape velocity of something. Okay, so we look at that and say, well, gosh, we ought to be able to now solve for things. So the escape velocity of the moon. Okay, so if I want to find the escape velocity of the moon, well, I know that the escape velocity is square root 2gm over r, and so I just got to plug in the values for that of the moon. Well, we did this in previous problem, right? So we know, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The mass of the moon is going to be 7.34 times 10 to the 27 kilograms. And then the radius of the moon is 1.738 times 10 to the 6 meters. And so we find the escape velocity of the moon is going to be 2,430 meters per second, or in other words, 2.43 kilometers per second. So the example we did before, we were leaving at 2,000 meters per second, so that was less than the escape velocity, and so that means that it went up really high, but then the moon's gravity could pull it back down again. So this is a derivation of the equation for escape velocity, square root 2gm over r, where r is the radius of the surface of the thing. Now I should also point out, this is another interesting thing, and that is if you were in orbit around something, the escape velocity from orbit is going to be less than the escape velocity from the surface. That's because this is a bigger r right there. And so this is one of the strategies possibly for building an interplanetary spacecraft is do the high energy lift to bring the parts into orbit, assemble it in orbit, and then fuel it, and then it takes less fuel for it to go. And so that might be easier than launching from the surface, simply because the escape velocity from orbit is less than the escape velocity from the surface.